Hello guys, I welcome you to the channel Nota Bene Tech on Tube yet again with a video discussing in theory some of the concepts related to the aerodynamics. The subject taken now is boundary layer from the book which is Fundamentals of Aerodynamics, and also it is in the semester course of IIT Kanpur, and I'll just going to explain the concept with the help of a definition and with the help of the graph and obviously the related properties. And in the next video we're going to discuss the equations of the boundary layer, but right now the definitions and properties will be discussed. So let's see what we have as far as the boundary layer and the concept in this video is concerned. Definition: the boundary layer is a thin region of flow adjacent to a surface where the flow is retarded by the influence of friction between a solid surface and the fluid. So that is the flow. Okay, the boundary layer is a thin region of flow. It is normally a region of flow, and obviously between a solid surface, which is maybe in the, obviously this is the aircraft, and the fluid, which is the air surrounding the aircraft. So it has been in the shadow graph is in front of you. The boundary layer is the thin region of flow, and it is between the surface and also between the air, and it is retarded. The flow is retarded by the influence of friction. Okay, there is no such friction. We have to consider or ignore the friction between the two between the surface and between the fluid. Properties: velocity and temperature profiles. Number one, this property, as in the video is in front, the graph is in front of you. That is here it is represented as V of V infinity into temperature, which is velocity and temperature, and we have taken it T is equal to TE. Okay, that is the outer edge of thermal line. Okay, and this is the outer edge of velocity, which is velocity temperature line, velocity thermal line, and we're going to deal with the velocity and the temperature with the help of these outer edges. Okay, VW is equal to 0 starting point, and which is T is equal to TW, and which is now we're going to discuss it in as a rho into tau into W, and also that is the lambda, and lambda is the distance between the surface and the outer edge for velocity, and this whole area obviously that has been outer edge of thermal, so this whole area is temperature, this whole area is the distance, and this whole area is the thermal lambda T, the distance to the temperature. So we're going to say that U is equal to, which is velocity 0.99 of U of E. UE is the velocity at the outer edge of the boundary layer. Okay, so we just have to this is the UE at the, so that would be multiplying by 0.999, we get the U, and lambda is the velocity boundary layer thickness. This is the velocity boundary layer thickness. So the properties of the boundary layer thickness has also been actually discussed, which is the third property, boundary layer thickness. So lambda is the velocity boundary layer thickness, and lambda T is the temperature boundary line thickness. So that is the two temperature profile has been created, velocity profile within the boundary layer. Okay, so that is the velocity profile within the boundary layer, at which is normally starting point at 0, and it has TW is equal to T. Okay, so that also been created by the Q of W. Okay, and these this is also been created by the velocity and also by the temperature. So these are the two profile, velocity and temperature profile, has been considered by the shape lambda T as well, and also by UE, and we have now, which is V, velocity and temperature. So these are the two major properties of a boundary layer or the profile. So we have created with the help of the graph. So normally this is velocity boundary layer thickness, U is equal to Uy, okay, and also y is equal to 0 and y is equal to lambda over here. Y is equal to lambda, y is equal to 0, and by the help of that we're going to drive a function which is u is equal to u of y. Okay, so that would be a profile created in terms of the function, and also we have the profile created in terms of the function of temperature and the function of velocity. So this is how we're going to discuss it. Now we're going to discuss with the help of which is the shear stress and heat transfer. In general, normally lambda temperature is not equal to lambda, which is obviously we have discussed. This one is shorter, this one is larger. The relative thickness depends upon the Prandtl number, and which is Prandtl number. It can be shown that if PR is equal to 1, then lambda is equal to lambda t. If PR is greater than 1, then obviously if PR is greater than 1, then lambda t is less than lambda. If PR is less than 1, then lambda t is greater than lambda naught. So these are normally the parameters. If the number is equal to 1, then we say that the two actually distances or the thicknesses, the velocity and the thickness are equal. The thickness is greater by the two profiles are actually equal, and if this one is greater than 1, then obviously temperature profile or the thermal profile would be less than the velocity. Or if this one is less than 1, then obviously that condition that we are discussing right now is this one. If PR is less than 1, then lambda t is greater than lambda. So that is in the graph as well. The consequence of velocity gradient is shear stress. So what is now, after we have discussed the velocity and the temperature, the consequence of the velocity gradient is shear stress at the wall, which is represented by this, which is tau of W is mu, or which is derivative of mu over derivative of y. This is known as the velocity gradient at y is equal to 0. And similarly, temperature gradient at the wall generates heat transfer at the wall. Similarly, temperature gradient at the wall generates heat transfer at the wall. So we have got the shear stress, which is this, with the help of the velocity gradient. And now we're going to have the temperature gradient, which is this. Normally temperature gradient is this, and we're going to transfer the heat and generates heat transfer at the wall. So this QW is the heat transfer, and this which is tau of W is normally the shear stress. So this is the shear stress, and this is the heat transfer. These are also the similar properties that we have discussed, the shear stress and the heat transfer. So you have to keep in mind, earlier if I actually not clearly mentioned, but obviously with the help of the explanation of the properties, this one is the shear stress generated by the velocity gradient, and this one is the heat transfer generated by the temperature gradient. And temperature gradient is what? dt over dy. Okay, so, and also minus k is represented as an energy. So QW is equal to, that is QW is also discussed as a wall. So we have to discuss as a wall. So earlier, so where this one is the temperature gradient at y is equal to 0, similarly as in case of velocity gradient, which was this at y is equal to 0, and we have got the temperature gradient at y is equal to 0, that is at the wall. Okay, so the W is that is at the wall. In general, both T, which is this one, because of this is the shear stress, and QW heat transfer are functions of distance. Absolutely right. And from the leading edge, that is this and this, which we have concerned so far. We have earlier in the property one, which we have discussed, that we have to just explain it in the terms of profiles, will also be created in the terms of functions. And now we have created the shear gradient and the velocity gradient so velocity gradient and the temperature gradient are also the functions and of distance, and that is why that is our main task as far as the boundary layers are concerned. The third is displacement thickness. Fourth one, I believe, is the displacement thickness. We have discussed the boundary layer thickness as well. Okay, and we have in terms of velocity, in terms of temperature, and also we have created the profiles in terms of functions. We have we have discussed this one, and also we have created the shear stress and heat transfer because with the help of the velocity gradient and also the temperature gradient. So we have discussed three properties. The displacement thickness is like this. It is in front of you. It is from 0 to y1, 1 minus rho of velocity into rho e into ue, which is derivative of y. So this is how we're going to say it. So this is velocity, this is rho, and dy is displacement at y is equal to 0. Edge of boundary layer is this one, y is equal to y1 over here. Okay, this is the wall. So this ue is also also represented as rho of e. So this lambda star is an index proportional to the missing mass flow. So this is mass flow, which is the displacement thickness. Okay, this is the, because of this displacement thickness we have created the mass flow which is missing. So it is an index. Okay, so this index, this is an index which is proportional to the missing mass flow. If it's higher, obviously the mass flow, the missing mass flow will also be higher. So that is directly proportional. So it is one of the properties. That how we're going to actually discuss it with the help of the theory, and due to the presence of boundary layer. Okay, so normally this is the missing portion due to the presence of the boundary layer. So let us explain. Consider point y1 above the boundary layer. This is y1 above the boundary layer. Okay, and as shown in the figure, consider also the mass flow, which is the unit depth perpendicular to the page across, we have discussed it, is the perpendicular across the vertical line connecting y is equal to 0 and y is equal to y1. Then A is equal to the actual mass flow between 0 and y1, which is represented by this rho u dy. Hypothetical mass flow would be between 0 and y1 if boundary that is B. So that is the hypothetical mass flow. So layer were not present. When the layer is not present, obviously we have the actual mass flow because of the actual mass flow between 0 and mass 1, 0 and y1, and hypothetical mass flow as well. So when the layer is not present, that would be the missing mass flow, and it is represented by lambda e, that is the index. So that is the decrement in mass flow due to B minus A, present of boundary layer, that is 0 to y1, rho of E, mu of E minus which is rho and u, taking the difference. Obviously the hypothetical mass flow and the actual mass flow will create us the difference, which is the missing mass flow in terms of lambda e. So express this missing mass flow as the product of this and a height of lambda e. Obviously this is an index, so this is a missing mass flow. We're going to multiply this, okay, which is equal to this, and when we're going to actually solve it out, we get the same index equation for the missing mass flow, or because of the displacement thickness represented by the index, which is lambda star. So this is how we're going to deal this one. So the momentum thickness and the laminar and the tubular flow are also in the same category of the displacement thickness. With the help of actually explaining some of the other two graphs, we can help them explain. If you are actually interested in explaining me these two parts, I'll able to actually explain it in the help of the other video, and if it's requested, I'll normally going to discuss that. But right now I'm going to end the property function of the boundary layer along with the definition. In the next video, I'm going to explain the equations, okay, and also which are used in terms of Navier-Stokes equation normally, so we're going to discuss those as well. How we're going to use the momentum normally. The equation in equations, we're going to discuss these two properties as well, momentum thickness and the laminar turbulent flow, but we're going to discuss, if it's requested, as in properties of boundary layer in some separate video as well. So I'll end up my video. Hope to see you that you enjoy what I actually gathering or actually extracting from the books of fundamental aerodynamics, actually seeking knowledge, gaining knowledge, applying knowledge, and obviously just producing with the help of, or reproducing with the help of the videos, and also with the help of the notes. So I'll just end up my video. Hope to see you with another video, as I said, on equations of boundary layer. So till then, take care and have a nice day.